Okay, so this is going to be a review of fuel cells and reactions because looking through a lot of these papers, there are certain reactions that the IB likes to ask on paper three. Now, the good news is some of these reactions are given to you in your data booklet. So if you forget them, there's access to them, and I'm going to show you where those are. But I'm going to kind of talk about each of these fuel cells in the terms of reactions, kind of understanding how they work, and then where you can get the information from. So the first idea is what's called a hydrogen fuel cell. Okay, one that uses hydrogen gas to produce an electrical current by oxidizing it and then reacting it with the oxygen to form water. So the overall reaction of these is H2 plus 1 half O2 yields H2O. So obviously the benefit of a hydrogen fuel cell is that the only product that it produces is liquid water. And so that is definitely a benefit of not producing any greenhouse gases or any other byproducts from the reaction as well. Now, on the left here, you can see a diagram of a fuel cell. And I know it looks super complicated, but what's happening here is this. The way a fuel cell works is you have to feed it fuel to allow the electricity to be produced. And in a hydrogen fuel cell, you're obviously putting hydrogen gas into there. And so, as long as you have a source of hydrogen gas, the fuel cell will continue running. So, the benefit of that versus a primary cell that expires and runs out of energy, this can be a continuous supply of energy as long as you provide the hydrogen gas. Now, the big difference between these two fuel cells, alkaline and acidic, is the electrolyte. Okay, so the electrolyte kind of determines what type of reaction is going to happen on here. So when you have a potassium hydroxide reaction, electrolyte, excuse me, it's going to be undergo basic reactions. And if you do phosphoric acid, it'll be acidic half reactions. Okay. Now, the good news is that these reactions are located in your data booklet. So if you scroll to the table 24, where your standard electrode potentials are, you'll notice that there are four reactions that are listed here that involve um, hydrogen and oxygen gas. And so what you'll notice is that, remember, these are reduction potentials though. So only two of them are the correct direction and the other two are the incorrect direction. Okay. So the reductions here are the reduction of oxygen. Okay. And so what you'll see here is these two here. So obviously the one that produces OH minus will be the basic one, and the acidic one will involve H plus. Okay. The oxidation reactions are the reverse. So notice here, hydrogen gas in the reverse reaction being oxidized. If there's OH minus, that's the basic. If there's H plus, that's the acidic. And so you can kind of see this here. So when you have a basic reaction, okay, you are going to have the hydrogen gas reacting with, oh, excuse me, 2 OH minus to yield 2 H2O plus 2 electrons. And the oxygen is going to react with water and 2 electrons to form 2 OH minus. Okay. And again, if you notice, when you balance these reactions out, the electrons cancel, and you're left with essentially a net reaction of H2 plus 1 half O2 yields H2O. Okay. Also note that the number of electrons here is 2. And in case you need to solve for delta G later on, your N is 2 in this reaction. So remember, these two reactions are given to you in your data booklet right here. So you'll notice that the basic one here to form OH minus, and then the basic one here for the hydrogen oxidation as well. So again, this is, again, minimize what you have to memorize in here. So these you don't have to worry about. Sorry, my screen share kind of is acting up. Oh, there you go. Okay. So With the acidic, it's the same idea, but you've just got now this reaction. So instead of being in an OH solution, you've got H plus. So you notice these H pluses in the reactions instead. It still adds up to the same reaction, and it's still, again, overall, the idea is that you're, whether it's acidic or basic, you're converting hydrogen and oxygen gas into water. And so in this diagram, the hydrogen gas is coming in, contacting with the anode so it can oxidize. The electrons travel through the wire to the cathode to allow the reduction of oxygen, and the electrolyte allows the movement of ions from the cathode to the anode to complete the cell. And again, water is being produced um, when the um, when the ions are going across the electrolyte and then coming into contact with the H plus ions that are being produced, um, and then it's being removed from the cell. So hydrogen fuel cell converting H2 gas and O2 gas into water, whether it's acidic or basic, both those sets of reactions are found in table 24. So use that as a tool so that you don't have to memorize these reactions. And these are kind of common ones that they do like asking about. Now, um, the second type of reaction is a PEM, a proton exchange membrane. Okay. So this is still the same idea, but instead of a strong base or an acid as electrolyte, it is using this kind of polymer. And so it allows the movement of the protons across this membrane to react with the oxygen that's being reduced in the cathode to produce water. And so the only real big difference here is the movement of the ions across the electrolyte. So here you've got the movement this way, and then with the proton exchange membrane, you've got the actual hydrogens going across. Okay, and so you've got a generally speaking, a platinum catalyst at the anode that helps accelerate the reaction. Now, this reaction is the same as the water. So again, you're going to be transporting H pluses across, so you want to consider this kind of acidic. And so you're going to have that same, that same reaction that you had for the acidic hydrogen fuel cell earlier. So again, you don't need to memorize these reactions because the idea is that these are given to you in the data booklet. And so the only real difference between this is you've got um, this membrane that allows the movement of hydrogen through there. And so this is more reliable, and it won't kind of need to be replaced. Okay, so with the proton exchange membrane, everything works the same as a fuel cell. It's just that your electrolyte is different and it's transporting H pluses across from the anode to the cathode, but you're still converting hydrogen gas and oxygen gas into water. This type of fuel cell is the one that you find more often in hydrogen powered vehicles now. So this is the more kind of modern version of the hydrogen fuel cell that is more efficient. One of the cons about hydrogen fuel cells is that um, storing the hydrogen fuel cell is can be very dangerous. It's explosive. It's hard to store, um, and if there's any kind of damage to the containment, it can be very dangerous. And so, what the alternative is what's called a methanol fuel cell. Okay. And so a methanol fuel cell works in a very similar way with the proton exchange membrane of moving H pluses across the membrane, but instead of hydrogen gas being oxidized, methanol is oxidized. And so you can see that methanol will react with water to form CO2 plus 6H plus 6 electrons. Okay. You still have the oxygen reacting to form the water. And so overall, you're essentially combusting the methanol through this reaction. Okay. Now, um, what I'm looking at here is how do we try to memorize this? Well, I think the best way to do this is the oxygen reaction is still the same. It's still acidic. What I would look at is the methanol anode reaction. This one here, I would focus on the fact that you are converting um, methanol to CO2. And instead of memorizing the entire reaction, I would consider looking at this combustion reaction and splitting it up into two half reactions like you normally do with redox. So instead of memorizing these two half reactions, look at these at this reaction and split it up into its two half reactions. CH3OH goes with CO2, O2 goes with H2O, and if you balance the half reactions like you do in topic 9 and 19, you will get these reactions. So again, minimize what you have to memorize in these types of fuel cell reactions, but you are responsible for them. So I want to make sure that you are considering those in this. And so the overall reaction is really the one that you want to kind of focus on to split up um, into the half reactions for the methanol. So the methanol fuel cell works the same way as the PEM, the proton exchange membrane. Hydrogens are moving across, converting into water, but instead of hydrogen fuel, using methanol fuel. And so obviously, the benefit is that it's easier to store and transport liquid fuel methanol as opposed to hydrogen gas. But obviously, the disadvantage is you are producing CO2 gas as along with H2O in this reaction. And so you are producing some greenhouse gases in this reaction. Now, the last one um, is microbial fuel cells. And so this is an interesting way that scientists have come up with to convert organic matter in wastewater into electricity. And so the main idea here is that on the anode, there are bacteria and there's no oxygen kind of available here. It's anaerobic. And so these bacteria convert um, the waste into electricity. And so this one is a little bit harder. And so this is where we call the geobacter bacteria. That's what's at the anode right here. And so what it takes is it takes ethanoate ions and reacts with water to form CO2 plus H plus 8 electrons. Now, the same reaction on the cathode of converting the um, the oxygen into water occurs. And so you kind of see a pattern here, right? Like for the most part, oxygen is going to be at the cathode converting into water, whether it's acidic or basic. Most of them are acidic. There is one basic one we talked about at the very beginning, but this reaction doesn't really change. It looks a little bit different in each of these steps because the balancing is different, but overall it's the same reaction. It's 1/2 O2 plus 2H um, plus 2 electrons yields H2O. So the cathode reaction, all of these stays very, very similar. It's really the anode reaction that's really changing here. Okay. Now, the overall reaction of this is just essentially the combustion of ethanoic acid. So you're converting CH3COOH plus water. Oh, sorry, not plus water, excuse me, plus O2 to make 2CO2 plus 2H2O. Okay. And so um, this is the way a bacteria microbial fuel cell works. And so these are the reactions that I think you'll want to be familiar with. And so, good news one, the cathode reaction stays fairly the same in all these fuel cells, except for the alkaline fuel cell, where it's OH production with O2 instead of water from O2 with H plus. The anode one is where it really changes, but for the most part, they're just the oxidation of hydrogen, except with the methanol one, where it's methanol going to CO2, which you can balance on your own, and then the um, ethanoate ion um, reacting with CO2 to do this as well. And so there are a couple of reactions that you might want to know for this. But again, most of the reactions are listed in um, your data booklet. So don't worry about memorizing as much. I'm going to label these basic and basic. Your acidic and your acidic. So remember, two of them are oxidation reactions that are reversed. Two of them are reduction reactions that are actually occurring. So the oxygen, these two are the oxygen cathodes that you need to know for options. And these are the anodes that are two that you need to be familiar with as well.